Hello, everyone, and welcome back to part three of the Everything You Need to Know to Ace the new SAT Math section free masterclass here on YouTube. In this part of the masterclass, we are going to be going through the second content pillar, Advanced Math. So we're going to be working through a couple of different problems from this content pillar that will basically take you through everything you need to know under that branch, under that content pillar. So if you do want to follow along, I have linked the downloadable worksheet down below completely for free in the description box. And also, if you're interested in signing up for tutoring with me, those details are in the description as well. Thank you so much for watching, and let's go ahead and jump on in. Alrighty, so the first problem here is asking you to find all of the solutions to this equation right over here. So you may, if you know how to factor and all of that, you may immediately go, oh, okay, we're just going to set, it's already factored for us. Let's just go ahead and set x plus 3 equals 0 and x plus 5 equals to 0. And it's super easy to find an answer that way. But hopefully you did not fall into that trap because you noticed that over here on the right side of the equal sign, you saw a 15 instead of a 0. And so the only way that you can find solutions of an equation is that you want to find where they intersect the x-axis, or in other words, where y is equal to 0. So here we're saying that this expression is equal to 15. That's not okay. We need to make sure that everything is on one side and a 0 is on the other side. So to do this, we're going to use the same strategy that we talked about earlier, the expand and then simplify method. And if you watched the last part, you should already be familiar with this. So first, we're going to expand. We're going to expand this out using the FOIL method or just distributing all of these. So when you do that, you're going to get x squared plus 5x plus 3x plus 15. Then we're going to simplify. We're going to combine like terms. So we're going to combine the 5x and the 3x to get you x squared plus 8x plus 15 is equal to 15. Same number here. Again, the goal is to get a 0 on the right side. So what can we do to go from 15 to 0? We can subtract both sides by 15. And you end up with x squared plus 8x equals 0 because the plus 15 minus 15 cancel each other out. Okay? From here, now we can factor like usual. So we can pull an x out. You end up with x plus 8 equals 0. You can set x equal to 0 and x plus 8 equals 0. So x equals 0 is already the answer. To get x on its own here, you can subtract both sides by 8 and get that x equals negative 8. So these are the two solutions to the equation below. Alrighty, next problem. We want to solve the following systems of equations both graphically and algebraically. So let's start by solving it graphically so we can kind of understand our goal here with solving systems of equations. So let's call this first one equation 1 and the second graph equation 2. Let's start by graphing each of these points. So I'm going to set 0 to actually kind of be in the middle here. So this is 0, so this is 1, and this is negative 1. So in equation number 1, we have that the y-intercept is 1, and the slope is 1. And this is a line. So we're just going to graph that. So here's 1, and then here is a line with slope 1. Then, and of course, it would go down in the same direction. Okay. And then here we have a y-intercept of negative 1. But in this case, there is no slope because we're looking at a quadratic. You see the square here? That tells you that that is a quadratic. So when you have a quadratic, you know that it's going to make the parabola shape. So it's either going to be an upwards parabola or a downwards parabola. And there's a few different ways to find out what it is, but the most basic way of doing this is we can basically just plug in values for x. So let's plug in, we know that at 0, At 0, it's -1. What about at 1? At 1, we're at 0. What about at 2? At 2, it's 2 squared, 4. 4 minus 1 is 3. So now we have a couple of points here. Let's go ahead and graph this. So at 0, it's this. At 1, it is 0. At 2, it is 1, 2, 3. Okay. And then at 3, it is 9 minus 1 is 8. So at 3, it's 1, 2, 3, 4, 5, 6, 7, 8. So I think this is good on this side. Let's graph a few more points on the other side. So let's start at -1, -2. So if you plug in -1, you're still going to get 1, which is 0. If you plug in -2, you're still going to get 4, which is 3. So you're going to see the exact same pattern here. So you'll see this, and this is right here, and this is up here. So here you have an upward parabola shape. And all I did to graph this is I plugged in some points. So usually, whenever I have students that get confused about plugging in points, and they often ask me, well, how do I know which points to plug in? How do you know what to plug in? Well, the way I typically do it is I start by plugging in 0 because that's right in the middle of everything, of the positive and negative values. What's in the middle of positive and negative is 0. So I always start by plugging in 0 and just find out what happens because that actually tells you a lot about the behavior of an equation or a graph. So I do that, and then I pick some values on the left side and the right side of 0, which means a few negative values and a few positive values for 0. And that will give you an idea for the shape and the general behavior of the graph. And that's exactly what we did here, right? We started by plugging in 0 for x. And what I mean by plugging in, I put it in here where x is. So the -1, I got that by doing 0 squared minus 1. That's -1, right? When I plug in +1, I get 1 squared minus 1. That's 1 minus 1, which is 0. So that's how I'm getting those numbers. And I know what numbers to plug in because I'm just picking some small, easy to compute numbers around 0 that once I graph them do kind of tell me a lot about this. Okay. So, when you want to find the solution for a system of equations graphically, our goal, so graphically, we want to find the x values at which the graphs intersect. Yes? So in this case, we have this point right over here, and we have this point right over here. Okay? So what are those points? Well, we have, let's see, so this is 0, 0. So we have 1, 2, 2, comma 1, 2, 3. Right? So we have this point right over here. So it intersects at 2, comma 3. And then it also intersects right here, which is at -1, comma 0. -1, comma 0. Okay, so we want to find the solutions we want to solve. So those are the x values. So we would know that x is -1 and 2. So this is the graphical way of solving this system of equations. Now let's do it algebraically. Okay, so to solve it algebraically, we're just going to set them equal to each other, right? So we have y is equal to x plus 1 and y is equal to x squared minus 1. Well, they're both y's, so which means that they have to be equivalent to each other. So x plus y is equal to x squared minus 1. Okay, x plus 1 is equal to x squared minus 1. So how do we solve this? Same idea as everything else, right? We want to bring all of the values to one side and set it equal to 0, and then we can factor, do whatever we want. And we're doing this because I notice immediately that this is a quadratic, which means that that's the best way to solve for x, is to get it into factorable form or standard form, right? Which is, of course, this, ax squared plus bx plus c equals 0. This is what we call standard form. And once we're in standard form, we can factor, we can use the quadratic equation, we can do a lot of other things to solve for the value of x. So we want to get it to the standard form. And we know that we want it in standard form again because it's a quadratic, because we see the squared here. So let's move everything over to the right since we have the x squared on that side. So I'll subtract both sides by x, subtract both sides by 1, and you'll end up with x squared minus x minus 2 is equal to 0. And as you can see, we are now in that standard form, right? Okay. So now we can identify different ways to solve for x. First thing I would always recommend doing is looking and seeing, is there a way that you can factor this expression in any way? The biggest things I would look for are, your basic factoring things. Are there any factors that you can pull out? Is this a difference of squares situation? Is there anything you can cancel out? Stuff like that. Looking immediately, or is this a perfect square situation, or something like that? Looking at this immediately, I don't see any of those patterns, so we can go into solving using the quadratic formula. So if you remember the quadratic formula, there is a song that you can look up online. So that's x equals to negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, so in order to find x, we need to know what is a, what is b, and what is c. That's pretty easy. Those are just the coefficients of each of those numbers. So we know that a is the coefficient of x squared. In this case, that's just 1, because when there's no number, that means that there is a 1. b, b is just the coefficient in front of the x. So a coefficient in front of the x is negative 1. C is the constant at the end here. In this case, that is negative 2. So that's negative 2. So then we're going to plug in 1, negative 1, and negative 2 into our quadratic formula right over here. So negative b is negative 1, which is positive 1, plus or minus the square root of b squared, negative 1 squared, minus 4 times 1 times negative 2, all over 2a, which is 2. So you end up with 1 plus or minus. Negative 1 whole squared is 1, square root of 1, plus 8 over 2. So that's 1 plus minus square root of 9 over 2, which is 3, right? So, and then 1 plus 3 is 4. 4 divided by 2 is 2. 1 minus 3 is negative 2, and negative 2 divided by 2 is negative 1. So as you can see, we end up with the exact same values. We end up with 2 and negative 1, solving it in both ways. So again, the strategy that we're using here to do graphically is you want to pick points that are close to 0 so you can easily get a sense of what the points are and what the graph behavior is, and then find the points at which the two graphs intersect, and their x values of those points are the solutions. To solve graphically, or to solve algebraically, you're going to set the two expressions equal to each other, since they're both equal to y, which is the same thing. Once they're set equal to each other, we can recognize the fact that this is a quadratic equation. So we want to get it to standard form and then factor and solve for x like that. So we adjusted, we subtracted both sides by x and 1 so we can get it into standard form. We identified what a, b, and c are. We plugged it into the quadratic equation to find that the solutions are 2 and negative 1. Let's go ahead and do another example of something very similar so you can get a better idea of what exactly we're talking about here. So this is the same idea. We're going to call the first one equation 1 and the second equation 2. We're going to use Christmas colors this time. Let's start with graphically again. We want to graph both of these, but of course to graph anything, we need it in the form of y equals. So our equation 1 is actually not in that form. So that's our first priority, is to get it into a graphable form. And since we're looking at a linear equation, that means we want slope-intercept form, or y equals mx plus b. So which means we need to get y on one side and everything else on the other side. So in this case, y is already over here, so we just want to move the x to the right side of the equal sign. To do that, we're going to subtract both sides by x, and we'll get that y equals negative x plus 3. Okay? Equation 2 is already in graphable form because we have y equals something, right? Y equals something, which means we're good. We're in graphical form. One thing I do want to notice here is that we do have another quadratic equation, which means when you're graphing, you should expect that parabola shape again. Okay? So let's go ahead and take a moment and graph these now. So I'm going to be a little bit smarter about the line that I picked this time to graph. Usually they will give you a labeled graph, but let's just call this what it is. And then negative x plus 3 means that the y-intercept is positive 3. 1, 2, 3. and you have negative x, so the line is going this way. All right. Now let's graph the quadratic. Same idea as before. We're going to start by plugging in x is equal to 0. So when x is equal to 0, you have 0 squared plus 0 plus 5. That gets you 5. Now let's plug in some values around it. So let's start by plugging in some positive values. So if I plug in positive 1, I get 1 squared plus 1 plus 5. That'll be 7. If I plug in 2, I'm going to get 2 squared plus 2 plus 5. That's 4 plus 2, which is 6, plus 5, which is 11. Once I get to something that's really big like this, that's when I like to stop. Let's go the other direction now. Let's plug in negative 1. So negative 1 squared plus negative 1 plus 5, that would be 1 minus 1 plus 5, which is just 5. If I plugged in negative 2, you would get negative 2 whole squared plus negative 2 plus 5, which is 4, minus 2 plus 5, which is 7. So negative 2 is 7. And then I bet you if I plugged in negative 3, I'll get 11. But let's test that. And the reason why I guessed that is because if you see a pattern here, it's a little bit symmetric. And that's the idea of what a parabola is. But don't get too wrapped up in that if that doesn't click right away. So negative 3 squared is 9, minus 3 plus 5 is 11, right? So negative 3 is 11. So we can graph these, right? So 0 is 1, 2, 3, 4, 5. 1 will be 7, 5, 6, 7. And 2 is 11, so that's like way up here somewhere. Okay. Then we have negative 1 is 5. So 1, 2, 3, 4, 5. And then negative 2 is 7 again, and then negative 3 is all the way up here. So we're going to have something like this. And then let's go ahead and plug in negative 1/2. And the reason why I'm doing that is because I have a feeling that we have a sort of vertex right there. So if I were to plug in negative 1/2 squared plus negative 1/2 plus 5, I would get 1/4 minus 1/2 plus 5, which is basically 1/4 plus 5. So it's just a little bit under 5, basically, is what they're saying here. Right? This is saying it's a quarter. This is the same thing. I'm just flipping the order here. It's just a quarter less than 5. Yeah? So this is going to look something like this. So, in this case, graphically, what are the solutions? Are there any solutions? Well, looking at it like this, it appears not. So far we can say that there are no solutions, looking at it graphically. And that's because nowhere here does it intersect or does it look like it's going to intersect? Because this green graph is going to keep going up, up, up more, right? This maroon graph is going to keep going up, 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 wider like this, right? So it does not look like it's going to touch or intersect at any point. Let's test if this is true by solving algebraically. So to solve it algebraically, we're going to do the exact same thing. So we have y and y, so we can set both of these things equal to each other. Equals x squared plus x plus 5. Now we have a quadratic, so we want to get into standard form. Since x squared is over here, I'm going to add both sides by x, and I'll subtract both sides by 3, so you can cancel. And we end up with x squared plus 2x plus 2 equals 0. Okay, great. Now let's try to solve this. Is there any way that we can solve this? Again, looking for a way to factor it. I don't know about you, but I don't see a way to factor it. So again, let's go ahead and use the quadratic formula. So to use the quadratic formula, we need to identify what is A, what is B, and what is C. So A is the coefficient of x squared, which is 1. B is the coefficient of x, which is 2. And C is the constant at the end, and that is 2. So again, remember what is the quadratic formula? It's negative b plus or minus square root of b squared minus 4ac all over 2a. So let's go ahead and plug this in. So x is equal to negative 1 plus or minus the square root of 1 squared minus 4 times 1 times 2 all over 2 times 1. Yes? Okay. So we have negative 1 plus or minus the square root, 1 squared is just 1, minus 4 times 1 times 2 is 8 over 2 times 1. So here you should identify what's going on. You see that 1 minus 8 gets you a negative number. It gets you negative 7. And you cannot take, oh my goodness, you cannot take, the square root of a negative number. This does not exist. Therefore, again, the solution does not exist. There is no solution, right? We confirmed what we saw graphically by trying to find solutions algebraically. And now that we see that both agree with each other, we can be confident in our answer that there are no solutions to this system of equations. All right. The next problem is to simplify the following expressions using exponential operation rules. So, if you remember exponential operation rules, you should know that if you have if you're multiplying two exponentials with the same base, right? The same number in the base, the product of this, when you multiply the two, the product of this will be the same base and the exponents will be added to each other. Okay? This is the rule we're going to use here. There are several exponential rules that you should know for the SAT, but this is the one that you need to know for this particular problem. And the reason why we identified that this is the rule that we need to know for this problem is because these two bases look awfully similar, right? 3 and 1/3. They look very, very similar. How can I make 1/3 into 3? Honestly, vice versa too, but I don't like fractions. So how can I make this go from a 1/3 to a 3? 1/3 is the same thing as 3 to the negative 1 exponent, right? So I can literally rewrite this that way. So I can go, this is 3 to the negative 1/5 power times 3 to the negative 1 power to the negative 2/5 power, right? This right here is the exact same thing as this 1/3 that you see here, which is why you're able to rewrite it in this way. Okay, so the first thing I would do then is I would take these two, multiply them together to get 3 to the 2/5 power. And then, of course, you still have your 3 to the negative 1/5 power from earlier. And now we can use this rule here. You keep the same base of 3, because now they have the same base, and you add the exponents. So negative 1/5 plus 2/5 is positive 1/5. So this is going to be the answer. All right. Alrighty, now let's simplify this expression using exponential operation rules. So same idea, but different type of problem. So the first thing I see is a quadratic, and it's a quadratic that's basically in standard form. I know it's not equal to 0, but you only need to set it equal to 0 if you want to actually solve for x. But as long as it's in this ax squared plus bx plus c standard form, it's ready to factor, right? You only need it to be equal to 0 to solve for x. The first thing that's ringing in my head is there a way to get this quadratic expression in the denominator to factor? So let's think about it. So for me, I'm thinking 1138 and put the negative there. So, okay, so yes, I can get it to factor into x minus 3 times x plus 8. Okay. And let me know if you want more videos about how to factor. There are many different types of factoring. The interesting part about the advanced math content pillar of the SAT is it actually covers several subjects of the SAT, or sorry, several subjects that you learn in high school, right? It covers basically geometry, algebra 2, pre-cal even, right? The SAT goes up to pre-calculus. So there's a couple of different subjects that are mishmashed in here, which is why it's not really that feasible to go through every single thing, or like every single small skill rather. But you will definitely see factoring on the SAT. So if that's something that you struggle with and you'd like to see more videos on, definitely let me know in the comments down below, and I will be sure to make that happen soon. Okay, so I've factored this denominator, and then I can keep, oh my gosh, okay, and then I can keep the x minus 3 here in the denominator. Okay, now you might see something interesting. There's an x minus 3 here, and there's an x minus 3 here, both in the denominators. So how can I make them have a common denominator? By tacking an x plus 8 onto this one, right? So to get that to happen, I'm going to multiply the top and the bottom by x plus 8. So you get 7 times x plus 8 over x minus 3 times x plus 8. And then this part is 3 minus that. Okay, let's go ahead and factor. We're going to use our same expand and simplify method here. So we're going to expand. You end up with 3, 7, negative 7x minus 56 over x minus 3, x plus 8. This gets you 3 minus 56, which is negative 53, minus 7x over x minus 3, x plus 8. All right. And at this point, there is pretty much nothing else that you can factor out, I believe, because I think 53 is a prime number. So this is pretty much the answer. This is the fully simplified version of this expression right here. Alrighty, let's do the same thing again. This time we have a quadratic in the numerator and in the denominator. So we want to factor both of these to the level best, right? So for the numerator, I'm thinking 2, 3, both of them. Yep. So we have x minus 2 and x minus 3. And the denominator can factor into x minus 2, x plus 3. Okay, x minus 2's cancel, and you end up with x minus 3 over x plus 3, which is the fully simplified version. Okay, so again, if you are new to factoring, the idea here is that you want to find numbers that multiply together to get c and can be cross-added and multiplied to get b. So in this case, in the numerator here, I identified two numbers, negative 2 times negative 3, which add to get positive 6. And when I cross multiply, 1 times negative 3 is negative 3, and 1 times negative 2 is negative 2. When I add those things together, I will get negative 5, which is b here. That's how I picked out that 1 is the coefficient here, negative 2 is the coefficient here, 1 is the coefficient here, and negative 3 is the constant here. Okay, same idea with the next one. I said, okay, to get negative 6, it'll still be 2 and 3, but I need a negative on one of them. So the negative is either going to go on the 2 or it's going to go on the 3. But when I do the cross multiplication, 1 times positive 3 is 3. 1 times negative 2 is negative 2. When I add them together, I'll get positive 1, which is the coefficient here, which is b. So that's how I know that this is the order, because if I had done 2 and negative 3 and cross multiplied them, I would have gotten 2 minus 3, which would have gotten you a negative number here, and we want a positive. So that's why this doesn't work, and you want to go with this method right there. Okay, again, if you want a more in-depth explanation of factoring, let me know and I can make that happen. Also, there are a couple of different ways of factoring. Some people, they do this exact same logic, but they write an expression out in the middle. So you would write out like, let's see here. So for the numerator, for example, you would write out x squared minus 2x minus 3x plus 6. And then you would factor out the x here, and you would get x minus 2, factor out negative 3 here, get x minus 2, and then you would get x minus 3 times x minus 2. This is the exact same idea, just in some steps. So some people do it this way. I learned it the butterfly method. If y'all ever went to Kumon, then you might know. So whatever works best for you to understand and to really identify those patterns, go ahead and just go with that. Okay? All right, let's do another one as simplifying. So again, we have a quadratic. I want to factor as much as possible. In this case, it's not traditional factoring, but I do identify that I can pull out an x from here. So when I do that, I get 6x plus 5. And then in the denominator, there's not much we can do. It's 3x plus 1. There's nothing really that I can pull out, or no other changes that I can really make. So this is basically as simplified as it's going to get. There's nothing I can cancel, nothing more I can factor. The way that you know that you're done simplifying something is I look at each term, right? So this is a term, x is a term, 6x plus 5 is a term, and 3x plus 1 is a term. Each of these terms cannot be factored anymore, so we know that we're done simplifying. All right, let's find the solution of this equation here. This is dealing with square roots. So remember that when you have two things with the same base, so same square root, the coefficients can just be added and subtracted together like they were coefficients of variables, basically. So when you see like square root of 2, for example, let's just call anytime you see square root of 2, let's just think of it as a variable x. And anytime you see square root m, let's just think of that as the variable y. And all of the other math can be done with that exact same mentality. So this is like you're looking at a y, and then the square root 2 again is like you're looking at an x. So what can you do here? Well, I would want to combine my terms. I would want to combine x's, and I would want to combine my y's and have them on either side, right? So let's combine the y's first, or let's go ahead and call the greens x's, because that actually makes a little bit more sense for what I'm doing here. Let's get our x's together first. So 7x and 2x, I can subtract both sides by 2x, and I get 5x, right? So I get 5x minus 6y equals 4y. So now I can add both sides by 6y to get 10y. So 5x equals 10y. Now let's go ahead and put back all of our variables as they are. So you'll end up with 5 square root m equals 10 square root 2. Okay, we want to get m by itself. How can we get m by itself? First, we're going to divide 5. Get square root m equals 2 square root 2. And then to get m by itself, we want to square it. So square, because that's the opposite of square rooting something, is squaring it. So I'll leave you with m as equal to 8. Right? All right. Finding the solution of this expression right over here, anytime you see absolute values, you know that you're basically dealing with with two expressions all at once, right? You know that 3x plus 8 could be equal to negative 16, and 3x plus 8 can be equal to positive 16. And we want to solve both of these expressions. So here we can subtract both sides by 8. and get 3x equals negative 24. X is equal to negative 8. And then on this side, subtract both sides by 8. You get the 3x equals 8 and x equals 8/3. And we can check to make sure that this work makes sense, that this is correct, by plugging these numbers back in. So what happens if I plugged in negative 8? I would get the absolute value of 3 times negative 8 plus 8, which is absolute value of negative 24 plus 8, which is the absolute value of negative 16, which is positive 16. So this works. Let's try the other option. If I were to plug in 8/3, I would get the absolute value of 3 times 8/3 plus 8, which is the absolute value of 8 plus 8, which is the absolute value of 16, which is positive 16. So again, it works. So that's how we can confirm that that these are the correct answers. So again, anytime you see the absolute values, it's very simple. All you do is you split it into two separate equations that you're trying to solve, one with the negative version of this number and one with the positive version of this number. Okay. All right, what are the sum of solutions? So all this is asking you to do is same thing as before. You want to find the solutions, and then once you find all the numbers, you want to add them together. That's all. That's the only extra step here. All right. So again, we want to bring the m's together, right? We want to bring the variables together, the common terms together. So to do that, the first thing I'm going to do is I want to get rid of the square root, first of all. So let's focus on that first of all. So square root of 6m minus 26, and I'll subtract both sides by 3, and you'll get m minus 3. I'll square both sides so that I can get rid of that square root like I wanted to, and I'll end up with 6m minus 26 equals m minus 3 whole squared, which let's go ahead and expand that out. So you get m squared minus 6m plus 9. If you don't know the whole squares, your whole squared expansions, that's something that's really important to do so. So here are the formulas. Make sure that you know them and you understand them. So in this case, we are using the second formula right over here. Okay, that's what we used to simplify or to expand this out. Okay, now we want to bring, now that we know it's a quadratic, right, we want to get it into standard form. So to get into standard form, I want to bring everything over to one side and end up with a 0 on the other side. So I'm going to subtract both sides by 6m and add both sides by 26. And when you do that, you'll get m squared minus 12m plus 35 equals 0. Okay. And can you factor this? I think so. I see 1, 1, and 5, 7. And you can make both of them negative right here. And you end up with m minus 5, m minus 7 equals 0. So m equals 5 and 7. But again, your final answer needs to be the sum of those solutions. So the final answer is actually going to be 12, right? The sum of the solutions is 5 plus 7, which is 12. Okay. All right. We want to find the solution. Again, we want to find what k is. K right now is on the denominator, which basically makes it a sitting duck. So there's a lot of situations, right, that make things sitting ducks. An example is when the variable is in the denominator. The variable is inside of a square root symbol. The variable is inside of something else, right? When they're in those sitting duck positions, the first priority is to get them out of the sitting duck position. After that, if you're dealing with a quadratic, you want to get into standard form as soon as possible. And if you're dealing with a linear, like you are in this case, then you want to isolate the variable as soon as possible. So our first priority is to get rid of the sitting duck situation of the 4k minus 3 in the denominator. How are we going to do that? We're going to multiply this entire expression by 4k minus 3. When you do that, you'll get 2 times 4k minus 3 equals 11. Right? Basically, the denominator will cancel. Then we're going to, again, do the expand simplify method in order to isolate the variable. So we're going to expand. You'll get 8k minus 6 equals 11. And then we want to isolate the variable. That's our simplification here. We'll add both sides by 6 to get that 8k equals 17. So k is equal to 17 divided by 8. All right, and that's the solution. Alrighty, so the expression 4 times 3 to the t power gives the number of leaves in a tree since it's been planted. What does the 4 represent in this expression? So this is a typical exponential format. So you will see this in context of interest sometimes and interest problems. You will see this in terms of exponential growth and decay sometimes. So this is kind of like a real world situation that you might see. So when you have something that is in exponential format like this, typically you will have this first item is called the principal. Okay? As in your school principal. Inside the parentheses, you will have something about the rate of growth or decay. And this t, the variable, represents time, which is typically the x-axis. It's typically the independent variable. So in this case, what is it telling you? Well, it's giving the number of leaves since it's been planted. So what this is telling you is this is the initial amount of leaves in the tree, and it's growing at a rate of 3, basically. So not 3 per year because that would make it a linear relationship, but exponentially, right? The rate is 3. So the 4 represents the initial number of leaves when planted. Okay, this function represents the population. This is another way in which you'll see exponentials seen. In a fictional town, Maysville, T years after 1998. So based on the function of the population, what was the population in 2021? So years after 1998 means what? It means that the 680 that it provides, it's the initial population, but it's the initial population when? This is the population of Maysville in 1998. And T is the number of years, and this it gives you, right? T is the number of years after. And the P of T, which is what you want to find, is the population at a given number of years. So how many years? Well, how many years since 1998 is 2021? You're just going to subtract those, right? This is an occasion where using your calculator is probably going to be pretty helpful. So you're going to subtract 2021 minus 1998. And I get 23. Okay. Could you have done this in your head or manually? Of course, but it's just easier sometimes to not use that brain power and use your calculator instead. But just be very judicial about it. If it would have been easy for you to do it in your head, do it in your head and don't waste your time on the calculator. Okay, so 23. This is telling you that it's been 23 years since 1998. So T is 23. That is the only information you need now. Now you know that you want to find the population 23 years after 1998. So you're just going to plug that in here. This expression is going to go straight into your calculator. So when I do that, I get 163.85. Okay, so this is the population. I believe there's supposed to be a 1 here. My apologies. Because if this is less than 1, then that means that the population is decreasing, which is what you can see here. So if I plugged in 1.94, there we go. You should see that you get a much larger number. You get 2.83 times 10 to the 9th power, which means like way like in the millions and billions of population here. Sally opens a new savings account and deposits $500. The savings account earns a 2% interest rate compounded annually. How much money will be in Sally's account in 5 years given no other deposits or withdrawals? So this is another example of exponentials. For a case like this, we're going to use the formula A equals P plus 1 plus R, or times 1 plus RT. Again, this is the amount in the account. This is the principal amount. Same idea as before, principal. And this is the rate. R is the rate. So 1 plus R is what's going to be in here, and this is the time that has passed. The reason why this given no other deposits or withdrawals is really important is because it's saying that like we're not going in and changing the principal at any point, and we're not changing any other factors. So the 500 that she added in there, that's all that we have added in there, and the rest is all going to be interest, and that is never going to change. So yes, this is an overly simplified version of what you would see in the real world, because in the real world, you would have a savings account and deposit money, but you might withdraw some of that money to use for some major expense, or you might keep depositing money regularly so you can build the amount that's in there in addition to the interest that you receive. So this isn't entirely realistic to the situation, but it does make our math easier. So we want to find how much in 5 years. So what that's telling us is T is 5. It's telling us that the principal is $500 because she put $500 in there originally. We said that R is 0.02 because that is 2%. That's a 2% interest rate. So let's go ahead and do that. So we have the principal is 500 plus 1, or times 1 plus 0.02 to the 5th power. And you can literally plug this expression straight into the calculator. And when you do that, you will get 552.04. So $552.04. Okay, that is the amount that she's going to get. So in other words, she has made $52.04 in interest. So that's the cool part about opening up a savings account, right? Okay, this is the last problem of today. So the function below models the height, h, in feet of an object above the ground t seconds after being launched straight up in the air. At how many seconds after launch does the object fall back to the ground? And what is the best interpretation of the vertex of the graph of the equation in the xy plane? So this is actually asking a couple of different problems here. You might have also seen this in your physics class if you took AP Physics. This should be a pretty familiar setup for you. So the main question, the math that we need to do here is how many seconds after launch does it fall back to the ground? So h is the height, right? Let's understand the equation that we've been given us. So h is the height of the ball after t seconds. So t is the time in seconds. Okay, so obviously at time equals 0, which means basically as it's being thrown or right before it's being thrown, the height is 0 because it has not been thrown yet. It's still at the ground. But then what happens? The height will increase until it reaches the top, and then it will fall back down. And so if you notice, it's making a sort of parabola here. So it's asking you, it's a parabola, which means this is a quadratic. Okay. So if it's a quadratic and we're asked to find when does it fall back to the ground, we're trying to find the other time at which h is 0. So we know that this is time equals 0. We want to find what is this time. So what is this problem? You want to find the solution of this quadratic. Well, we know how to do that, right? We know how to do that. We need to get this quadratic into standard form and set it equal to 0. Well, it's already in standard form, right? There's no constant, so that just means c is equal to 0 in this case. But we can set our expression in standard form, negative 16t squared plus 64t equals 0. And now we can solve it, right? So in this case, I can take out a negative 8t, and I get 2t plus 8. And I can actually pull out another 2 then, in that case. So I get negative 16t will get you t plus 4 equals 0. So t is 0, and t, this becomes a negative inside. Yep. And t is equal to 4. So we already know that t is equal to 0 is a solution. This 4 is what we're looking for. So how many seconds after launch? 4 seconds after launch. This is the answer that we're looking for. Okay. The best interpretation of the vertex of the graph. So this is the graph that we're talking about here, right? This is the vertex of the graph, the parabola, the maximum, whatever you want to call it. What does this represent? This represents the maximum height that the ball goes when it's thrown, right? So that's the kind of answer they would be looking at if this was a multiple choice problem. All right, y'all, that is everything I have for you guys today. Thank you so much for tuning in for part 3. Make sure to subscribe and turn on the notification bell so that you get notified when I post a new video, the next part of this masterclass. Like I mentioned earlier, my socials and resources for this masterclass are linked in the description box down below. And feel free to scan this QR code if you want to provide some more feedback about how you enjoyed this masterclass. Thank you so much, and I'll see you in the next one. Bye.